isolated. I don't know about everyone who's attending, but certainly most of the Eliiza crew is in Melbourne, and so we are feeling lockdown 2.0. This week for the Virtual Brownbag, we have a wonderful presentation on time series data from Markus. Just a quick reminder of, standard Google Hangout online e-meeting etiquette is if you guys could turn off your videos and be on mute to sort of minimize the background noise. If you have questions throughout, please feel free to put them in the chat function or to just note them down and save them until the end. I think we're just about ready to get on the road. Yeah. Hold on. I'm trying to do something fancy. There we go. All done. But please, yeah, feel free to sort of put any questions into the chat. This is really about learning and us sort of sharing our knowledge with you, our community. And so there's really no such thing as a silly question. And to kick all this off and to teach us a whole bunch about time series data, and I've had a look at these slides, so I know they're great. You guys are in for a treat. I'd like to just hand over to Markus.
Right, welcome everyone. So I'm giving you a tiny primer on time series today. And to start with, what are time series even? Time series are data that allow us to forecast the future. And they are an incredibly valuable area to master in data science because they're so prevalent. Think about the weather. You will need a forecast. What is the stock market going to do? You will need a forecast. Am I going to be hungry? You can even forecast that, and many other things. And time series have one advantage that is at the same time also a disadvantage over other data. They have structure. They have a relation to other variables at the same time and across time. So for example, if you look at the time arrow here, you have a measurement which says 3 at some point, and you have other measurements at other points in time. And these can be related to other measurements happening at the same time, but they're also related to themselves in the future and the past. The difficult bit about time series is that you can only use them in one direction. If you are at time step t equals 5, it is not of interest to know what happens at time step t equals 1. It's already in the past. You will only want to look into the future. So you are effectively limited to work in a causal way. And unfortunately, that is one of the serious limitations. You are at a struggle to get data because time only passes serially. You cannot speed up time. If you think about computer vision, it is easy to get 10, 100,000 photos by just sending 10, 100,000 people out there to take photos. With time series, you can only get them as time passes. Right. So let's look at the first univariate example, where we look at a single time series. And as we can see here, it's a temperature series, which has its ups and downs. And judging by where the temperature peaks are, this should be in the northern hemisphere. And judging by the temperatures, probably somewhere in Central Europe. And what we can already tell here is 3 things. Firstly, there's a certain seasonality. We see an up and down which repeats periodically. Secondly, we have a certain trend. If we look at the values in 2010, they're lower than in 2019. And thirdly, we have noise. All of the squiggly bits at the top and at the bottom of the series. It's not just one neat line. In order to describe this time series data, we will need to master all 3. Right, let's take a first very, very simple effort. And in data science, simple, if it works, is always the best. And what we're looking at here is an average over the last 4 years. So we take the values of 2010, 11, 12, and 13, and use that as a value for 2014. And as we can see, this simple average based on the last 4 years already yields quite good a description of the data. And the advantage of such a method is, if you want to, you can implement it directly in your data warehouse or data lake in SQL. And if you have terabytes and terabytes of data and have to do millions of predictions a day, it will probably already be sufficient and be an amazing tool. If you think, for example, about Kohl's doing a daily stock forecast, what do we need to order next week? They will probably have 100,000 items, but they will probably also have 2,000–3,000 stores across Australia. And if you think that each of these forecasts is just going to take 1 second, then you're already looking at quite a lot of forecasting. And if you go for more involved models, they might just not be quick enough. So a very simple tool, but always very powerful. But then again, we want to do data science, and we don't just want to take the past 4 values and make a prediction out of it. We actually want to understand what is going on. And one such way of going about it is dissecting the time series into its components. And as a first step, we can just take one value for each year, fit it with a linear line, because we do seem to have a linear trend here, deduct it from the original, and can split it up into detrended data and a linear trend. And from the looks of it, works actually quite nice. So what can we do next? Oh, sorry. Yes, I've already talked about this. Next, we want to get rid of the seasonality, this periodic up and down corresponding to the seasons, to summer and winter. And as we have a nice example, what we can do is we can just fit a cosine function to the data, as you can see here in orange. And the residual that remains after deducting both linear trend and the cosine seasonality fit from the data is this tiny bit of blue noise at the bottom, just between plus and minus 5C. So it's already quite good a description. So what can we use the last residual bit of noise for? If we look at a heteroscedasticity, sorry for that complicated tongue breaker, then we can use it to have an understanding of how the future time series will develop. And what heteroscedasticity means is, if we have heteroscedastic time series, then the mean and the standard deviation for this time series is not constant across time. But fortunately, what we are looking at here in the green is the variance, and we can also see that the mean from the blue curve are fairly constant. So what we have here is a homoscedastic time series. So we can use this in a last step to estimate the error of our model. And combining all three, what we then have is both the model in orange and in paler orange certain error. A confidence interval. In this case, the 2 sigma standard deviation. And since we're still talking about very simple models, we want to understand what is going on. What we effectively have here is a combination of seasonality, trend, and noise. And in our case, it was just a simple linear combination where they were added on top of each other. But there also is the possibility that they are a multiplicative combination of the 3 of them. And if you look some of the more advanced tools, which do not just use a linear trend and cosine fit to the data, like, for example, the stats model TSA ARIMA, or, for example, the profit packages, what you will get is more along the lines of this package here. And you can see the description within the 1 sigma standard deviation is much better for the data. And the reason for this is that it takes a more detailed, fine-grained look at the data. It doesn't just look at the general trend over the 9 years of the time series and then predicts for the 10th year. It looks in details at what happens in between. And so for the seasonality, for example, you can see that it is not just a cosine curve, but you also have some smaller features going on inside of it. And the more details you have, of course, allow for better description. Right. There are also slightly more involved univariate time series modeling choices out there, like ARIMA, GARCH, Gaussian processes, but they all effectively work on a single time series. So the question is, what is left for us to do? We can't just finish this talk after 2 minutes. And of course it is explaining the variation in the data, because at the moment we do understand what will happen, but not why it will happen. Right, let's take a first look at something that will lead us to a multivariate approach, depending on several variables. And what we have here is the ASX 200 opening prices. And we can see here in 2019, there's a nice and steady rise, and in March, a massive drop. An economist would tell you that prices depend on demand and supply. And we also have the trading volume curve here, and it seems to be fairly steady. And then for some reason, it just also dramatically spikes. And we can only wonder about where does this movement come from. We can try and fit it into our previous model. Here I used again the profit package. And what we see is it's not a really good description at all, which you can especially see by the ballooning error out here. So what causes the spike? Here, of course, as we know, the corona pandemic is at fault. And it already tells us two things. Firstly, for our time series, we have to consider concept or data/corona drift, and we also have to keep causality in mind. What we modeled previously was time series with the data just from that one time series. But what we can see here is that if we just take this blue data, we will not be able to model this drop. What we have to account for is that there are other data which result in this drop. Right, but the stock market is a really difficult topic, and if you're able to model it well, you will be a very rich person. So let's look at something more easy that we can quickly cover in this talk. The weather in South Australia and the electricity production. So why are the two related? If you look at this graph here, you can tell that during some hours of the day, the green and the yellow make up a lot of the electricity production, and they correspond to solar and to wind power generation. And of course, we cannot control the weather. At the same time, the total production depends on both of them. So they will be an ideal case to candidate to showcase some of our tools that we have in our bag to analyze time series. But to make it even more interesting, we won't just look at the total production and try to predict the total generation. We will look at the time series. And you will notice, at the price time series. And you will notice that the price series has certain spikes, and most of them correspond to generation peaks, which happen to mostly be around 9 and 5 p.m., just before we go to work and just before most people return from work, because that is when we just use up the most electricity. But some of them, they also coincide with before or after. And in this time series itself, it is fairly benign because at the moment we are in the middle of winter, and that's just what it is. But if this were a day in summer, then what we can often see is that there are massive spikes when the temperature increases due to everyone turning on their air conditioning. And there can also be days in summer when the sun is really beating it down and we have a lot of solar electricity generation, or possibly a lot of wind. And thus the price all of a sudden drops, because the price can also go negative for electricity. Unfortunately, not for most of us customers, but it can go negative. Right. The most important tool that you will probably want to look at are correlations. They are incredibly powerful, and they yield values between plus and minus 1. If you have a value of plus or minus 1, it shows you perfect collinearity. +1, it means that it increases at the same trend as your underlying data. -1, it does the exact opposite. And at 0, you have the absence of a relationship. Sorry, the absence of a linear relationship. So for example, if you look at the schedule generation in South Australia, it has a -0.5 correlation with the wind speed in South Australia, which means that if the wind is really, really, really blowing, the schedule generation tends to be lower. Right, so what this is effectively a very quick tool for variable screening. Do we see some potential here, or is there none at all? For example, if we want to predict the prices, then looking at cloud cover seems to be a bad tool because they have a 0 correlation. But there are some shortcomings to correlations, and firstly, they are really prone to outliers as they depend on the standard deviation. And secondly, they are linear correlations. So if you want to look at linear trends, that's fine. If it is a non-linear relationship, possibly not the best tool. Moreover, with time series, what you have to keep in mind is that they match the entire time series, at one point in time. But what we possibly also want to consider is, do previous values influence our time series that we want to predict for? And what comes in handy there are cross correlations. And what they give you are the correlations between two time series lagged by a certain value. And they are a powerful tool to scan for hidden temporal connections. Let's, for example, look at the correlation between the temperature in South Australia and the price of electricity in South Australia, lagged by several hours. And what we can see here, if we go for a lag of 0, there is not that high a correlation between the two. It is somewhere just around 0. Yet, if we go for a lag of about 18 hours or so, then all of a sudden we see a nice spike in correlation. For example, I assume this could be caused here by a glut of solar electricity, and by possibly people turning on their AC, thus resulting in such a spike. But what we can also do is we can look at another tool that comes in quite handy with time series, finite differences. And what you do for the finite differences is just take the difference between a time step t and its previous value. And what we can see here is there are even more trends which are coming out now from, for example, wind speed to the prices, which were not visible at all before. And yeah, they're actually one tool which is not implemented directly in Python. But if you want to implement it, you can easily do it like so. Take one time series and its correlation to another time series shifted by a certain lag. And here I opted for about 48 different lags, resulting in that corresponding plot. Right. I've already mentioned that correlations are a linear tool. There are, of course, also possibilities to make the correlations slightly nonlinear, going from the Pearson's to the Spearman correlation. But effectively, what they are is a linear tool. If you look at this is a nice parabola, and everyone will probably agree there is a clear relationship between what we have on the x-axis and y-axis. Yet, if we look at the two correlations, they are respectively -0.13 and -0.18. And we're looking at the same data. And what we're seeing here is, firstly, that we have this vulnerability to outliers where the larger time series in blue shows the lower correlation. And second, that despite one data perfectly explaining the other data, we can actually not see it in the correlations. And for these cases, there are different tools, and I cannot really go into detail because there's a lot of them, so I will just list a few. There are causality tests, there are information theoretic approaches based on entropies, copulars, and mutual information, and others. There are the finite differences in other transformations which can make them more handy. Imagine, for example, we take the square root of this data here. What we will then see is a perfect correlation, and we can nicely model our data. And there are other more advanced options. But what we always have to keep in mind is more specialized means more powerful, but it also means we need to be more careful that they actually are suited to the task that we want to model. Right. Data science, we don't just want to look at data, we also want to model data. And one of the most common tools used for time series are LSTMs. They are recurrent neural networks, specifically made for such tasks. And what they do is they hardcode the time-like nature of data into the network. They don't just take the data at one point in time and then make a prediction out of it. What they do is they also take into consideration previous points in time. They then connect all of them and provide as an output the data for the next point in time. However, due to the nature of lots and lots and lots of parameters inside of this, and due to the sluggishness to respond to data, you need lots of it. And what I looked here at, the weather data, which I did the correlations on, was about 2 months worth of data. At hourly rates, that's not a lot of data. What you need more like is more than 10,000 rows of data, a lot. Moreover, due to the nature of each calculation depending on the previous point in time, they're not easily parallelizable, which means they're not the fastest thing out there. And that also comes in when you do run inferences. But if you want to read more on this, there is an excellent blog post by Chris Kohler, which I can really recommend to you. But next up, our first predictions. And I use Gluon TS here, and what you will see is the predictions are actually rubbish. If you put in rubbish data, you will get out rubbish results, and the best model will not help you. What it has done here is one of the most common pitfalls that I see with time series data. If you look at the real data, you have this spike here, you have a valley, another spike, a valley, and a spike. And that is actually precisely what a model does here. It has a spike, a valley, a spike, a valley, and another spike, and then it goes down. So what the model has learned is not to predict the future. What it has learned is to minimize the error, but just taking the values, I think that's about 2 time steps back, and using it as the input for the next few steps in time. Cheeky. So what you always have to keep in mind is that when you get an error, for example, in computer vision, it will give you a certain idea of what is going on. If you get an error here, you have to be extremely careful, because there are pitfalls like this, where the error might look small and it looks like you actually have quite good a description of your data, but it is not. And of course, this can come in many variations. I think between the two of them, I changed just one variable. And I didn't do any data treatments. I just put in temperature, wind, and I think cloud coverage, very little in data. The last thing here that is really important to notice, what we have is not just a time series output by the model, we also have a certain confidence interval. And for time series, they are really, really important. If you, for example, want to predict how much Vegemite Coles is selling, it doesn't just matter to know that they're going to sell 5 jars of Vegemite in Australia tomorrow. It also matters if it is 5 jars plus or minus 20, or is it 5 plus or minus 1? Because if you want to order, you will need to adapt accordingly. Another model that I quite like are the Wavenets. Is the Wavenet architecture, which is based upon dilated convolutional neural networks. And what is underneath it is causally padded convolutional neural networks. And causal padding means that you take all the data up to your point in time where you currently are, and everything into the future will be just zero padded. Instead of values, you will just have your zeros. And this architecture has several huge advantages over LSTMs. For example, due to the nature of it, you can easily parallelize. And moreover, because you don't have to keep all of the past states in memory, you also have low memory requirements, which makes it easier to model. You can possibly go for deeper models, and you will have much faster models. But what does it actually look like? That you can see here at the bottom. You will have inputs. For example, here we are at a point t = 0. And you have time steps going back 16 points into the past. And what you have is, on top of it, dilated layers. And dilation means that you take into consideration not just this value at t = 0, but also past values. And if you stack multiple of these layers on top of each other, you can go for bigger and bigger and bigger dilations. And the higher the dilation is, the more of the past you take into consideration. Right, so what did we get out of it? As we can see, the modeling is already a lot better than with the LSTM, because I added a tiny bit more data. I still didn't do any intensive feature engineering or anything else. And as we can see by the scale, we are mostly within about $10, $20 of the actual price per megawatt hour. And that is already quite good. And what I took into consideration here was everything up to 32 steps in time back, which roughly corresponds to 1.5 days, give or take. And again, we also see the errors here, the 2 sigma standard deviation, and it is just an error of the forecast. The actual data might be outside. And I've already mentioned that this architecture is quite fast, and per epoch of training, I think it took about roughly 2 seconds on a single CPU core. And if you have about 2 months worth of data, as I used for this simulation here, it means that you can train on, give or take, about 900 rows of data in under 10 minutes for about 500 epochs, which is quite nice, because quite fast. And it gives you an accurate description of the data. What this specific modeling effort suffers from, though, is that it is still not best at modeling spikes. And I've purposefully omitted some of the spikes in the data, which I've previously mentioned. For example, if you turn on your air conditioning and everyone else turns on their air conditioning, prices will go up because demand is massive. So despite very little effort, we've already achieved quite good value. If we wanted to get better, what we would have to do is find better causal relationships. What actually causes the price to change? We can explain quite a lot of it simply by looking at the weather, but as we can tell from this here, it is not a perfect description yet. Right, as a summary, real-world time series data can be dealt with quite easy tools. As we've seen, a simple average was already a good description of the first data set. And if it is already a good description, then often we should just stick with it because simpler is better. But what we have to keep in mind then is that if shocks are coming and we do not have a model that explains the causality, like for example Corona, then all of a sudden we will be out of toilet paper. We have looked at quite a few tools that model the relationship between different time series, and that is how causality can enter. If we find 2 time series that have a perfect correlation, that yield interesting values, if we look at the cross correlations, if we look at causal testing or any of the other informations, then we will have a good time series to model our goal time series. But unfortunately, there's no tool that is a catch-all. You always have to be careful what you're doing, and you have to actually take a look at if the description is good. Similarly, you can't just throw all of the data in the world at your problem. Your model will just be slow. What you want is data that has a nice, clear causal relation to the data you want to model. And ideally, you want to have as little of it as possible. We saw two implementations of deep neural networks that modeled the time series quite nicely. And even on tasks like modeling the first time series that we saw, the univariate time series, they're now doing a lot better than some of the classical methods by up to 15%, according to recent, I think it was a paper in Europe's last year. And with very limited effort and some causally dependent data, we can already achieve quite good descriptions of time series that we want to predict. But what we always have to keep in mind is that we don't just want a prediction. We also want to have an idea of uncertainty. And the two tools I used in here are gluon-TS, which does it in a probabilistic Bayesian manner. And the second one, the Wavenet, I just wrote a quick script which implemented a quantile regression loss, which considers where are 90% of the values and which ones are outside, and correspondingly builds a certain error range. And with errors, I'm going to finish, and now it's question time.
Awesome. Thank you so much, Marcus. There've been a few questions coming up in the chat, and I'm happy to read them out. But if people want to unmute and ask them, that's perfectly fine as well.
Yes, of course.
Yeah, so Ike has asked your opinion on GRU versus LSTM.
Do you like apples better or do you like pears? I mean, I guess it depends on the task. If you want to make an apple cake, you will want apples or not pears. And probably similarly with LSTMs and with GRUs. I think the second one are gated. I actually forgot what the L stands for. Gated recurrent units. Yeah, but the idea behind both of them is very similar. The GRUs, if I remember correctly, are somewhat less memory intensive, but they are still very similar to LSTMs. So what I think is give it a try, but I expect them to be very similar.
Cool. Ben has asked an awesomely technical question. Could you describe the Wavenet as the weighted feature dot product combined with a time-based weighted average?
Oha. Sorry, give me some time to think about it.
It's all right. It means it's a good question, right?
Yes. So the first bit of the question, can you describe it as a feature dot product, weights times x plus some bias? Yes. What I'm wondering and struggling with is the time-based weighted average. And I'm not entirely sure how you mean it. Could you possibly elaborate a bit, Ben?
Might be easier if I just turn on my microphone. Can you hear me?
Yes.
Yeah, Ben.
Yeah, so it's just like a time decay. So it looks like there's just like the weighted average is a time decay system. So it's a neural network vertically and a time decay horizontally.
Yep.
So that essentially, so it's just a weighted average.
I understand where you're coming from. Yes, I see what you're coming from. But what you would be doing is absolutely possible, but what it would amount to is you first have a time series, and what you do with Wavenet is you approximate it. And then what you can do with your description of the problem is you do another approximation. And in this case, it is the approximation of the approximation of Wavenet. So yes, absolutely possible, but I assume it would probably be harder to train. And I think it is likely it would underperform.
Yeah, okay. I was just trying to figure out exactly what it was doing. So it's taking just so obviously taking more samples at that base rate and then keeping that. Yeah.
If we look at this slide, yeah, I mean, this is effectively happening. This is one of the calculations that happens for each of the data points, but it is effectively just one massive, but one calculation. The way time enters is by not just adding this t equals 0 data, but also adding all the data back to t equals minus 16 here, 16 time steps back. So it is hard-coded time series-like, but what it also is, it is indirectly time series-like, because you can just use the different past time steps and calculate for each of those time steps concurrently. Whereas I assume for your model, what it would do is, again, move back towards some, due to the time-based weighted average, some time-like nature, and it would be slower again because it would depend on past states.
So with this, what you have at the moment, would you, as you have t+1, t+2, would that be across 18 points, or are you setting it to 16 and it's traveling like a wave using that 16 points?
So this is based upon that we used a filter which has the step size of 2. We could also, for example, go for any integer number. We could go, for example, for n equals 1, and what we effectively would end up is no time series like nature at all, because all of these would just go straight up, straight up, straight up. We could go for n equals 3, where we would skip this point and go straight to the next. And it may be that depending upon how you choose those filters, you get a better or worse description. So it will have to be matched to the task. But it doesn't just have to be 16. It depends on how many dilations you choose, because the number of time steps you go back is dependent on your filter size times the number of dilations you choose.
Yeah. Lots to think about. Thank you.
Yep, pleasure.
Max has asked how you calculate the standard deviation, since they're not a direct output of the machine learning model.
Yes, I noticed it near the very end that I forgot to talk about this bit when it came up. So what GluonTS, which I used for this modeling here, if you have the time, take a look. It's absolutely interesting, because what they're saying is you never have to do any feature engineering again. In theory, we can do all of it if you supply us the right data. But that's not the most powerful thing about it in my mind. The most powerful thing about it is that it intrinsically has baked into it that it does some Bayesian probabilistic modeling underneath it to get those error ranges. Just answering in the chat at the same time. GluonTS. And the precise model architecture and how they get to these uncertainty estimates, you can read it up in this paper here. Unfortunately, it would somewhat stretch this brown bag if we were to go into detail here. But they describe it quite nicely in this paper here, how they came to these uncertainty estimates. And for the Wavenet, the way I implemented it is by using the quantile regression loss. And the quantile regression loss, what it does is it looks at not just our prediction and the true value, but it also takes a look at the different possible values. So that's a bad description. What it effectively does is, I actually think I might, no, I don't have it open anymore. What it does is it takes the mean of the maximum between the predictions plus or minus a certain quantile value. Again, I can give you a description which will describe it in more detail. Where did I implement it? Yeah, I think I followed this specific path here. They should give you an idea of how to get similar error estimates. But they will have to be tuned, and it is not just as straightforward as implementing them in this manner. Sorry, not always as straightforward as implementing them in this manner.
Okay. Dan and also Ben have sort of seconded this as to whether you can share sort of code around the South Australia power model.
I can, yes.
Yeah, cool. So we'll just make a note of that. Aaron has asked whether being a physicist has given you a different view of implementation on time series techniques, such as looking at causality, etc.
Interesting question. I mean, I've only ever been a physicist. I never studied economics or mathematics beyond a few lectures back in my university days. So I don't really know if it has influenced me in any way that I cannot obviously notice. But what it obviously has changed for me, and the way it most definitely influences my thinking, is if you think about these slides here, I don't just want predictions, I also want errors. As a physicist, what you always want is not just a quantity. For example, say the charge of the electron is 1.6 plus or minus a bag of sand. What you want to know is it's 1.6 to the 10 to the minus and units accordingly. You really want to have an idea of your uncertainty. I think that is probably the only obvious way that I can think of.
Okay. That's sort of the end of questions in the chat. So if anyone else has questions and they want to unmute for them, please feel free. I've got a little question though. When doing like correlation analyses, how do you distinguish outliers essentially from actual like sort of causative or meaningful correlation factors?
I had it in one of the previous versions of this presentation. There's a really nice homepage. Causation is not correlation. And what they give you is lots and lots of time series. For example, the rate of suicides and how many car accidents there were, or how many storks there are and how many babies are born. There is a lot of spurious correlations out there. A lot. You can match so many things, it's absolutely bananas. But you are right, at the end of the day, correlation does not imply causation. What you can do is take it through a modeling step, firstly, and see if it does have an influence. If yes, then you will have to think about it after if it's actually something that you want to model for. And with all of the future variables, what you have to keep in mind is that, for example, if you want to model I'm sorry, that's a bad way of describing it. If you want to, for example, model how many bottles of a soft drink are sold, that the number of bags of crisps sold is possibly a good description because people tend to consume both of them at the same time. So they will make our model work. There's a correlation, but there's no actual causation because buying a bag of crisps doesn't cause us buying a can of soft drink. they are more of a confounder, because the actual underlying reason is probably we want to be lazy couch potatoes, and we want to enjoy a nice film, and we want to really spoil ourselves. So in a certain way, using the data and thinking about it, asking stakeholders what they think, because feature engineering also does depend a lot on stakeholders. But beyond that, it is hard.
Oh, that's fair. Max has asked whether they're right, the examples of one-step forecasting. Do you have some advice or thought on multi-step forecasting?
So if you think about the univariate examples at the start, if you go for the averages, it is very easy, because you can just continue forecasting and forecasting and forecasting. They're effectively independent of it. With the models that I showed after, with deep learning models, it is actually quite tricky. What I have done in the past is train, for example, for different time steps, for different time step predictions. For example, say I create a model which is specialized on predicting for one time step into the future. I create another model which is based for 2 time steps into the future. But multi-step time forecasting, if you do it in the manner as the deep learning model that I've shown, it also depends on not just having the time series. It also depends on having the variables, the features that you used for the modeling. So for example, it doesn't just suffice to have price information. You would also have to have the weather information for multiple steps into the future. So I could be wrong here, I could be absolutely wrong, but I don't see how you can implement the deep learning methods in a manner that is similar to how you can implement the univariate modeling choices that I've shown before, and how they can just continue for an arbitrary length into the future.
Thanks, that was a really good answer.
Shark
I shouldn't sound
attacks and ice
surprised when I
cream
say
sales.
that. Robert has asked, what are your thoughts or strategies for dealing with time series data that contain rare extreme events such as 45+ degree days? My immediate thought, of course, was that I would just wait a few years until 45+ degree days and no longer that rare or extreme.
Yeah, but that is the cheeky shortcut. So what you normally assume is, for most of the tools that I've shown here, that what you do have is a completely benign set of data, and that the underlying distribution of data is Gaussian, that is normally distributed. So you have roughly a bell-shaped curve. What you're describing with 45+ degree days is you deviate from a normal distribution. And there are tools of dealing with such scenarios, but of course, as always, none of them immediately come to mind. If it is, as we're predicting, though, a certainty for the future that we are going to have more days which are going to be quite hot, I would probably try to account for it in a special manner. And specifically, I know this is a shortcut, which is a bit cheeky, but specifically if we're talking about the weather and we want to model the prices for electricity, weather forecasts are one of the best forecasts out there, probably, because we've been studying this as humanity for quite a long time, and we can nicely go, say, for example, 7 days into the future. We can go 10 days into the future. If you go beyond 3 days, the weather forecast will become somewhat inaccurate. If you go to 10 days, it will probably be, give or take, 10 degrees, but you will still get an idea. And I would probably try to build features on top of it to use these really uncertain forecasts to get an idea of how likely outliers are in the future. It is just minted for that specific problem. How I would deal with it if we didn't have this special scenario of really hot weather days, and predicting the prices for electricity. I would have to think on it.
Is there I mean, I'm sure there is a way, and you will tell me exactly what that is, to, depending on the amount of data, like if you don't have sort of an overwhelming amount of data, get the outliers to be spat out to you as well, to just kind of be like, hey, these are the outliers. The model is ignoring them for now, but, you know, alter your settings or your inputs or whatever to sort of allow for that.
It depends on what you want to do. If you want to predict for the outliers, don't exclude them. If outliers are not that important to you, then absolutely do discard them. But the less data you have, the worse your description will be, because what you are doing is an approximation, and the more data you have, the better you can make this approximation.
Okay, cool, thank you. That's all the questions in the chat for now. We'll hang about for a little bit longer in case anyone has anything else they want to ask. But otherwise, thank you so much for attending this brown bag, and I hope you have an excellent rest of your week.
Bye.